Welcome back to Forge College. I'm absolutely thrilled to be your guide through today's explainer. Now, in our last lesson, we did some pretty heavy lifting, right? We mapped out the entire contract surface of your Ethereum project, identifying every single storage slot, every entry point, and all those gas-guzzling hotspots. Well, today, we're taking that surface map and drafting a concrete, actionable architectural blueprint for Solana. We are tackling the title of today's explainer head-on, Design Considerations for Porting. We're officially leaving that old EVM mindset behind and fully embracing the blistering speed and parallel processing power of the SVM. So, grab your mental hard hats because we are moving straight from theory into construction.
We're going to tackle this complete renovation in 5 distinct phases. We've got our master blueprint index here. First, reshaping your state. Second, slicing up entry points. Third, swapping out dependencies. Fourth, walking through a marketplace example. And finally, drafting your actual design brief.
Okay, let's dive into Phase 1, reshaping your state, or as I like to call it, moving out of the EVM closet. Let's just face it, on Ethereum, we all have a little bit of a hoarding problem. Variables just live quietly and implicitly inside one single massive contract. It's dynamic, it grows endlessly, and honestly, it's a bit of a black box. But on Solana, it is a totally different ballgame. Data lives in explicit, entirely separate accounts. You literally have to pay rent for the space you take up. The size is fixed the moment you create it, and ownership rules are strictly enforced by the runtime. You really can't just throw things into the back of the closet anymore. You need specific labeled storage boxes. So to handle this massive mental shift, we rely on a really brilliant concept, the Program Derived Address, or PDA for short. Think of a PDA as a deterministic, totally predictable account that is derived from specific seeds, kind of like a user's public key or a unique listing ID. Instead of having one giant global mapping buried deep inside a smart contract, PDAs act as these highly efficient parallel data vaults that are perfectly tailored to specific users or entities. This right here, this is the secret sauce that actually allows Solana validators to process thousands of transactions simultaneously.
Moving right along to Phase 2, slicing up entry points. It's time to tame those monolithic functions.
Now that we've got our data organized, we really need to address those massive EVM functions you've got. There is a fundamental, unbreakable rule on the SVM. Transactions on Solana are atomic, yes, but they are strictly limited by compute budgets and the sheer number of accounts referenced. Because Solana forces these strict limits to maintain its sub-second speed, heavy, do-it-all functions simply will not fit into a single operation. If you try to port them directly over as is, you are going to hit a brick wall.
So the solution? You split the function. Let's take an accept bid function, for example. On the EVM, it does literally everything at once. But on Solana, it becomes a two-step dance. Step 1 is your verify step. It validates the signatures and locks the state by throwing a reservation flag directly on the PDA. Step 2 is the finalize step, which actually goes in, executes those heavy token transfers, and clears out the reservation. You still maintain perfect atomicity and security, but you break that massive compute load into nice, manageable, hyperfast chunks.
All right, Phase 3, swapping out dependencies. This is all about relaying the outside world. Your EVM contract probably doesn't live in a vacuum, right? It likely relies on external price oracles or other helper contracts, which means we need entirely new architectural wiring. You basically have 3 distinct choices on the menu here. First up, Cross-Program Invocations, or CPIs. These cost you a bit more in compute because everything is happening on-chain, but the payoff is zero latency. You get immediate synchronous data. Second choice, Oracle Relays. These save you valuable compute because a trusted relayer pushes the data to an account periodically, but it introduces a slight moderate latency. And finally, off-chain indexing. This gives you the absolute lowest compute cost possible, but you're dealing with high latency and some pretty complex trust assumptions. So you really have to pick the right tool for your specific job. Let's make this concrete with Phase 4, the marketplace example. Time to ground theory.
Let's step out of the clouds for a second and anchor all these abstract engineering rules. Looking back at that surface map we created in the previous lesson, we identified 3 major state buckets for a Web3 NFT marketplace. You've got the global settings object, the individual per listing structs, and the per bid records. We have to map these over to Solana. The global settings might honestly just be a single account, but the listings and the bids, that's where things get really interesting.
Those buckets create our very first major architectural trade-off. Do we consolidate or do we separate? Think about it. If we consolidate and embed the bids directly inside the listing account, we save big on rent costs. But the catch is, Every single time a new bid comes in, we have to serialize and deserialize that entire listing, which eats up a ton of compute. Alternatively, if we separate them into individual PDAs for every single bid, sure, it costs a bit more in rent, but it absolutely maximizes our parallel processing speeds because validators can hit different bid accounts at the exact same time. The right choice here entirely depends on your expected transaction volume.
And that brings us to Phase 5, drafting your design brief, building the final schematic.
You've weighed all the trade-offs, and now it is time to actually draft your brief. A robust design brief follows a very deliberate workflow. It's not a novel, it's an engineering schematic. You need to explicitly document your validated inventory, write out your chosen account strategy, and detail exactly how you plan to refactor those entry points. You also need to outline your dependency replacement choices, provide some hard numbers on cost and performance estimates, and finally lay out your migration phases. This document becomes the ultimate source of truth for your development team. But remember, a blueprint isn't actually complete without safety nets. For every architectural trade-off you make, you're inevitably introducing a new friction point somewhere else. Splitting a function into a verify and finalize step, well, that might mean prompting a user to sign 2 transactions instead of just 1. So you absolutely must document a mitigation strategy. What is your fallback plan for that user friction?
In practice, these mitigations are highly tactical. If you split handlers, use strict precondition flags so that Step 2 can literally never accidentally execute before Step 1. If your strategy requires creating a ton of separate PDA accounts, you need to build batched account creation utilities under the hood so it all happens in one smooth swoop for the end user. Simple mitigations like these prove your design isn't just theoretical, it's resilient, and it's actually user-friendly.
And just like that, your architectural plans are finalized. You've successfully taken a messy EVM surface map and turned it into a clean, highly performant SVM design brief. This perfectly sets us up for our next lesson, where we're going to get our hands dirty with implementation tooling and a concrete migration checklist. I want to sincerely thank you for joining me on this explainer. This was brought to you by Forge College, and I highly recommend you visit our website at forge.college to continue your transition from EVM to SVM and to dive even deeper into this amazing subject. So I leave you with this final thought. Are you finally ready to stop hoarding your data in monolithic contracts and actually start building at the parallel speed of light? I'll see you in the next one.